Hello, welcome to my lecture on community-driven metadata and ontologies for material science, with a focus on the key role that they have in the development and use for artificial intelligence tools. The plan of this lecture is to introduce a metadata schema for annotating computational material science data, and that was developed in the context of Nomad, Novel Materials Discovery Center of Excellence. The key message is that this schema is compliant to FAIR principles for data storage and stewardship, and it is community-driven, as it should. If you are listening to the lectures of this workshop in a chronological order, then you have heard about FAIR principles earlier by Berend Mons and Claudia Draxel, at least. However, in case this sounds completely new to you, let me say that the FAIR principles for data management and stewardship were introduced in a paper by Mark Wilkinson and many others in 2016. The acronym FAIR stands for Findable, Accessible, Interoperable, and Reusable, attributes that stored data and metadata should comply with in order to face the big data-driven challenges and fully exploit the potential, which is the huge amount of high-quality data that each scientific community produces. Some authors prefer to relate the letter R also to reversible or recyclable, as the symbol may also suggest. Let me preliminarily comment on what this four attribute involves, but I will come back in more detail along the whole lecture. Findable is related to the uniqueness of the metadata. I will come to the central issue of defining metadata in a couple of slides. Accessible implies that data and metadata can be actually accessed at some well-defined location. Interoperability is a key concept related to the usefulness of the stored data. It is connected to the idea of ontologies, to which I will come back later. Repurposable, recyclable, reusable, whatever you like, asks to metadata to be as descriptive as possible of each piece of stored information. What I am presenting today was started as a community effort in a workshop held at the beginning of 2016, close to the beginning of the Nomad COE, and predating the FAIR principle paper. The discussions held at the workshop inspired a paper published in 2017. The discussion topics have been updated and expanded in a workshop held about a year ago in Berlin, and I am working on a paper summarizing the outcome of that workshop, which should be submitted soon, hopefully. One working group at the Nomad FAIR DI workshop worked at the definition of what metadata are for scientific data, and more precisely in the context of material science. So we had data scientists and material scientists, of course, in the working group. The starting point was metadata are data about data. Very good, but not at all useful. In order to improve on the definition, let me first introduce the concept of data object, also known as information resource, which can be thought as a row in a data table. Let's suppose we have some calculation on some material. The columns of the table specify attributes of the data object that characterize it. This calculation has, for example, some unique identifier, UID. It is performed on some structure which is stored in a file called graphite.xyz. It adopts some physical model, density functional theory, with some specific approximation, and it yields a value for the total energy. The attributes, so the columns in this table, are data or metadata, depending on the context. In this simplified example, the calculated energy might be considered as data, and the UID, the structure, the method, are metadata that characterize and define the data. Note that the metadata structure is intentionally a kind of placeholder, or rather an identifier for a more complex object, that is a file containing in itself coordinates, chemical species, simulation cell parameters, and so on. Imagine now that the calculation produces as a result also another structure file, for instance, because there are forces acting on nuclei and these nuclei are displaced. So you have a new structure. This other structure will be considered now as data, but it could be also metadata for another data object. In addition, metadata may contain administrative information such as who has performed the calculation, when, on which machine, and so on. Finally, and crucially, metadata should contain information about the full provenance of the data. For instance, in this simple example, the attribute structure should be annotated in such a way to know where it comes from. For example, from an external database or from other calculations or randomly generated, you name it. The attribute method should contain information on which numerical implementation was used, and so on. Availability of the full provenance is important for the repurposing of the data. In conclusion, we can now define metadata as the attributes that are necessary to locate, fully characterize, and ultimately reproduce other attributes that are identified as data. The metadata include a clear and unambiguous description of the data and their full provenance. Let me now move more specifically towards the Nomad experience and how we design the metadata for our stored data. The first item to keep in mind is the establishment, since 2014, of the Nomad repository, a storage of input and output files supporting tens of the most used atomistic simulation codes. Thanks also to the contribution for large materials databases from US, you see the credits, the Nomad repository contains today more than 100 million total energy calculation. The repository is the basis onto which the rest of the Nomad laboratory is built. The input and output files stored in the repository, the information stored in the output files and input are converted into the code-independent format by means of scripts called parsers that map the raw information into a metadata schema that we have designed and developed, and which I am specifying in a few seconds. The code-independent data are then stored in what we call the archive. The specifics of the infrastructure are discussed in Markus Scheidgen's poster, which I warmly recommend you to visit. You will learn complementary information on what I'm presenting here. Later, I will suggest also another couple of posters where the concepts I discuss are examined in detail. Besides, virtually visiting these posters, you will meet the people who deserve the credits for what I am presenting. The archive is directly accessible via an API, and we have within the Nomad laboratory 3 well-developed interconnected access points called Encyclopedia, Advanced Graphics, and Big Data Analytics, respectively. Later, I will explain the main ideas behind what we call the Analytics Toolkit, that is the green box there. Let me now focus on the metadata schema that we have developed, which is the backbone of the archive. A computational material science data object revolves around the execution of some atomistic simulation code, which I model as a black box with some inputs and outputs. Here is the black box, for which one needs to provide some information for identifying it, such as the name, the version, but also which linear algebra libraries were used for compiling it, and so on. Next, one needs to provide information on the atomic structure onto which the calculation is performed. So coordinates, which atoms, cell vectors, topology, I mean bond topology, in some input these are needed, and so on. The physical model, exchange correlation treatment, or the force field, depending on which kind of calculation, relativistic treatment, and then down to the numerical implementation, all the details. The output of the calculation might be minimal, some energies, some forces, for example, or extended, so any observable that you can think it is meaningful to be calculated and then stored. Keep in mind that the input model may be also quite structured. For instance, one can have a perturbative calculation that is performed on top of a self-consistent calculation, or several physical models may be used in different regions of the simulation box, as it is, for example, the quantum mechanics, molecular mechanics, or QMMM approach. In summary, one can think at linked tables in which the attributes of the data objects are organized. Here, I schematically represent the output, the data characterized by the metadata listed in the 3 tables carrying information on the input structure, the physical model, and the atomistic code itself. We have given to our metadata schema, which we call MetaInfo, the structure as summarized in the previous slides. What does this mean? Well, I should mention that in a simple implementation of a metadata schema, metadata are defined with the so-called key value pair. Here we could have defined a set of key value pairs of the attributes of data objects in a rather unstructured way, as I have sketched in the slide. In MetaInfo, we capture the hierarchical interconnection among metadata in the following way. First of all, we define different types of metadata. The two most important types are type section, which correspond to the tables in the previous slide, and type concrete value, which corresponds to the items in the table. Each metadata has several attributes, such as a unique name, a human readable description. Unique means also that each metadata can and indeed is identified by a unique string and also by a unique resource locator, a URL, which makes it accessible in the FAIR sense. Other attributes are the parent section, the physical units when it is a numerical value, and so on. We therefore come up with a hierarchical scheme that we describe as a posteriori, in the sense that it is built in order to store all the information that it is contained in inputs and outputs of computer codes by organizing the information in a logical, code-independent way. The opposite strategy, where one lists all the objects attributes to be found in a given data objects before doing the schema, that would be called a priori. Here I show again the tables with the actual section names as is defined in MetaInfo. The ideas that I'm explaining now are presented in the 2017 paper that I have already mentioned earlier. MetaInfo can be browsed at the link shown in this slide, where we provide also a graphical representation that displays the connections among the metadata. The core of the schema has a section run, which contains sections for the method and the geometrical information on the system, and the section containing the results, which has this strange name of section single configuration calculation. The latter is contained in section run, but has reference to the section method and system that define the calculation parameters. This is done in order to have that each section is contained uniquely in one section, but since it has information that are related to other sections, in order to avoid strange loops in the connectivity, we define these metadata that have a ref at the end. These are reference kind of metadata. Let me now just show one example of metadata that has name energy electrostatic, and it is used for storing electrostatic energy for some calculation. It has type concrete value. It has a readable description, total electrostatic energy, nuclei plus electrons, defined consistently with calculation method. If you go to the link shown above, you will see that this calculation method is actually a hyperlink, and you can follow what calculation method is, how it's defined, and so on. The data type is the floating point because it's a scalar that is defined by the type shape. That is, brackets means just scalar. Units are joule. It's an energy, so you expect that you use joule. Now, this metadata is contained in this section result, so single configuration calculation. I would like now to introduce another feature of MetaInfo which makes me move towards ontologies. As said, the core of MetaInfo follows the input and output of atomistic codes. However, the metadata have also meanings and logical or semantic connection that may be complementary to the main schema, made by section type metadata. We have therefore introduced another type of metadata which we call abstract type. All concrete type metadata are connected also to a hierarchy of abstract type metadata that capture and describe, for instance, their physical meaning, as in the shown case. It is the right moment for a practical definition of what is an ontology. An ontology can be described as a formal representation of the knowledge of a community with a purpose. Let me give a flavor of what these attributes mean. Formal is possibly the most important. It refers to the fact that an ontology is a machine-readable construct. It is a representation in the sense that the concepts, properties, their relations, functions, constraints, and axioms are explicitly defined. It is the representation of the knowledge of a specific domain, here, for instance, material science. It is consensual. And it is built to address specific issues, not to build a kind of theory of everything, even for a specific domain. So experts talk about competency questions that are actual questions that the expert of ontologies asks to the domain expert in order to build the ontology. What do you actually want from this ontology? So MetaInfo supports several types of relationships among the metadata, such as has-part, has-reference-to, has-abstract-type. In particular, the sort of alternative set of relationships among metadata introduced by the abstract types suggests that we can go further on building ontologies based on MetaInfo. Presently, we are actually building fully fledged dedicated ontologies on top of MetaInfo, and I refer to Maya Len's poster for more information on our activities. On the practical side, I have already mentioned that the data are mapped from the raw information stored in the repository into the archive by means of more than 40 parsers, one for each of the most used code in the community. We call this operation standardization. The data are still essentially unprocessed, with the exception of a conversion to standard physical units, independent of what is used in any specific code. We chose the SI units, a choice that should not need any justification. A next level of data processing is called normalization, which is still a work in progress and has the purpose of post-processing the data in order to store derived data useful for data analytics. To fix the ideas, the number density is derived from the number of atoms and volume of the simulation cell. Both quantities are certainly available from the raw input and output, but their ratio is normally not given. To make more concrete examples, we have normalization scripts for representing the electronic band structure along standard paths in the K-space, or space groups calculated via standard libraries on the basis of the atom's coordinate and cell structural parameters. I should now notice that MetaInfo has been designed also to be easily extensible. New metadata can be added following community awareness. The unique identifier of each metadata and the hierarchical scheme support the extensibility, and in fact, we have had many examples of added metadata. Derived metadata in the sense specified here, but also primitive when new parsers are developed. In general, this is used and will be used more and more to store descriptors. That is nothing else than the input for artificial intelligence modeling. So it's the numerical representation of a data object, a material, to make it short, in order that one can do artificial intelligence modeling. So when the community thinks that some descriptor is useful, it will be extracted from the calculated data and stored as a meta information in our archive. This leads me to the final topic for today, that is one of the main purposes actually for which MetaInfo even exists, which is allowing artificial intelligence analysis of the stored data. This aspect is taken care of by the Analytics Toolkit, which is accessed by the Nomad web page by the green link. So if you go to the web page, you see this stripe of boxes, and you click on the green one, and you get to the Analytics Toolkit. The toolkit features are described in details in Luigi's bylaws poster. In the poster, links are provided to actually put your hands today on what Luigi and I am describing. Anyway, I just highlight here the core ideas. Primarily, the toolkit gives access to the data stored in the archive and allows for their direct analysis in web-based notebooks. No registration is needed to access and play around, but with registration, users have storage space and can share their data analytics projects. We support popular libraries for artificial intelligence, for example, scikit-learn or Keras, if this means anything to you. But we also provide the code for recently introduced artificial intelligence methods. For both, we provide also hands-on tutorial to learn how to apply the method to materials science data. As an example of recently introduced methods, the method presented tomorrow by Mario Bolley and Runai Ouyang, for instance, have their respective tools and tutorials in the toolkit. Finally, and equally importantly, we provide notebooks that allow the users to reproduce published data analytics results and try different solutions. We encourage the community to adopt the same transparent strategy by adding notebooks reproducing newly published results to the toolkit. So this should bring the idea of reproducibility of data analysis to the next level. That is, you do some analysis on a huge amount of data, and then you make available the code that has led to that analysis that you published. So everybody can go and check, change some parameters, think, and maybe produce something further. I close now by summarizing the fair aspect of MetaInfo, that is the metadata infrastructure that we built for the Nomad archive. Thanks to the unique names and human readable descriptions, the metadata are findable. They are accessible via the unique resource locator, URL, through the API. They are interoperable because of the typed and extensible schema and the possibility to support ontologies. Due to the hierarchical schema, which supports the traceability of the provenance of the data, MetaInfo allows data analytics, so they are reusable. I thank the people here listed for the great work in developing and supporting, at all levels, the Nomad laboratory, and the audience for the kind attention.